first of all, thank you. It's really nice to be here. I've never been to IHES before. When I was looking, I thought that this was going to be a clock and that I would stop at a certain time, but it's actually a temperature. So I'm going to stop at a certain temperature. Let's say, actually it's rising quite quickly, so maybe I'll give myself until 30 degrees centigrade before I stop. Okay, so I'm going to give 3 lectures, and they'll be somewhat disjoint from each other. There'll be some general relation to KPZ, and really what I want to do is illustrate a few important ideas in KPZ, both phenomenologically and then mathematically. So I've kind of broken each lecture down, I don't know how to use this thing, into a physical goal and a mathematical goal. And actually, I think I advertised a different order for lecture 2 and 3, so I might actually switch the order when I give this. But so the first lecture is going to be about something called extreme diffusion, and the mathematical point is going to be to explain something about beta ansatz and the replica approach in relation to this model of extreme diffusion, and then to say something about how KPZ, in terms of the physical goal, is related to many particle diffusion. So, okay, so here's the beginning of the first talk. And I should say, this is joint work with the people on the side here. So Guillaume, who's at ENS Physics, my brother, who's an experimental physicist, his student Jacob, Pierre Ledussal, and then my students Hindi, Sayan, and Shalan. Okay, there's a good lesson in life, which is that when somebody claims that Einstein is wrong about something, they're usually a wacko. Okay, so really the point of this talk is to convince you that I'm not a wacko, or at least not about this subject. What I'm going to try to do is explain that there's an aspect of Einstein's theory of diffusion which I think breaks down, and I'll give you some evidence for why it breaks down. So essentially, the theory of diffusion was built around the behavior of single particles. And if you apply that theory to many, many particles, and you look at the extreme particles, the particles that kind of move the furthest and the fastest, I'll give you some evidence, and we're working on experiments to try to confirm this, that will say that their behavior is somehow anomalous compared to what you would expect under Einstein's theory, under essentially modeling everyone by Brownian motion. In the place of Einstein's theory, we'll develop a new theory, which will have some relation to KPZ, as I'll explain. And there'll be a new coefficient, which we'll call an extreme diffusion coefficient. And so the hope will be that this is real. It's certainly real to the models and to the numerics, but we're trying to see if it's real to physical systems as well. OK, so before I kind of talk about the theory, let me explain to you why does extreme diffusion matter. So again, just to be clear, what I mean is you have a system of many, many particles in a common environment, and you look at the particles that do the most, that move the furthest and the fastest. And so this is a slightly outdated picture. This was from when we were in the middle of COVID. This is the genetic mutation of different strains of COVID. Okay, and the x-axis is time, the y-axis is space. And you see that in this sort of mutation genetic space, there's essentially a random walk that's going on. There's some sort of process by which you keep changing and evolving. And the more that you evolve, the more the spread of COVID continued. And so there was essentially the trajectory of COVID was being driven by the extremes. It was being driven by the particles, by the versions of COVID that mutated the most. Okay, so this is certainly one piece of evidence that we care about extremes in systems of diffusion. Here, of course, it's not a physical diffusion. It's a diffusion in the space of genetics. There are, of course, many instances where we care about it in a more physical sense. If you take a pin and you prick your finger, which, I'll pause for a moment for everyone to do that. No. You'll feel something, hopefully. And that is the result of a transmission through all of your synapses of neurotransmitters. And you don't need to wait for 99% of the transmitters to make their way across for the signal to continue. You just need the first few neurotransmitters to cross all of the gaps. And so in this way, the way that you feel and the speed at which you feel something is about the extremes of a diffusive system. This is a much bigger version. This is a supernova, and there's a gigantic shock wave that's created in a supernova, and then there's diffusion of photons through the shock wave. And what we're able to witness and see from very far away are the photons that make it through the fastest and that go the furthest. So somehow there's also a sort of large number of particles, something like 10 to the 10 to the 40 particles, photons coming through this, and that we're only seeing some portion of them. Here's another example. This is some sort of internet, social web, or something of that sort. And we all know that it's the stupid ideas that catch on. And so the things that kind of define what is present on the internet are the things that kind of diffuse the furthest. The ideas, the memes, all of that sort of stuff. And here again was another picture from COVID. You see I haven't updated my slides in a little while. This is the beginning of COVID in Italy. And you saw that within the course of about a month, it spread wildly around the country. And it wasn't that people were coughing on each other and walking next door that was causing this. It was that people were getting on buses or airplanes or trains, and they were going far distances. So it was, again, the extremes in the diffusion of people that really controlled the speed at which the disease was spreading. OK, so hopefully, and you can create your own examples, but hopefully you believe that somehow extremes might matter when you're looking at large systems of diffusing particles in some sort of environment. Now, I just want to give you a sense of the scales. When we're talking about many particle diffusions, we of course can talk about scales that range quite wildly. On the extreme side, we have astrophysical scales, so 10 to the 60 photons, chemical scales, biological scales, and ecological scales. You should imagine somewhere, I would say, in the range of 10 to the 15 particles. The number of droplets in a sneeze or in your blood. Though, in fact, much of what I say will hold true to things like ecological scales. This is the movement of wolves in, I think this is Michigan, over time. Now, the important thing to take from this slide is that when you have a system of many particles diffusing in a common environment, if you have a theory that describes the behavior of 99.99999% of the particles, and you have 10 to the 15 particles, that leaves behind still a massive number of particles that are somehow unexplained by your theory. And so we're interested in kind of what is the signal, what is the information that's carried by those particles that are kind of beyond the scope of what you would call the typical or the bulk behavior of a system. OK, so in order to go in this direction, I want to kind of back up and just remember something about the physical origins of diffusion and remind you of what is Einstein's theory of the behavior of diffusive systems. So here you're seeing the behavior of little specks of pollen in water, and they're jiggling around. And people going back to Brown in 1828 observed this sort of jiggling motion. That's not good. Let's try this again. Well, I'll keep talking. So the basic idea was that you wanted to, so if you go back, then now this is 200 years ago, right? People didn't understand at all that there were water molecules that were sitting behind this whole system, right? And so what Brown did, and this was the genius, was that people thought that the reason why these particles were moving crazy was because they were essentially drunk, because they decided to move in a crazy manner, right? And so what Brown did is he took these pollen, which ostensibly is alive, and he stuck it in an oven and killed it, right? He burned it. So then he took what was left over, and he also took little bits of rock and dirt and stuff like that, and he put it in the water. And he actually observed the exact same statistical behavior, which convinced him that it wasn't something intrinsic to the pollen. It was something extrinsic. It was something acting on the pollen. It was the environment somehow acting. Now, what was missing to the picture was an understanding of what was acting on the pollen, right? And it took about 100 years, maybe 80 years, for the theory of molecules to be developed. People couldn't see water molecules at the time. They didn't have a resolution on microscopes for that. And so eventually what people realize is that, of course, you have these little water molecules bouncing around, and they're knocking into the much bigger tracer particles, the pollen, and that the result was this erratic motion. Okay? Now, what the statistical... I think we can just switch the order. What the statistical theory was that Einstein and others put forward was that each particle was going to behave like a random walk. Okay? You know, it was getting all these little kicks, and it was going to behave like some sort of random walk, or what you call it now, a Brownian motion. Okay? And so the model would be, the Einstein model would be to treat each particle as an independent random walker, and simply, you know, look at the behavior of those collectively. Now, already early on in this process, people realized that there were limitations to this theory of you know, Brownian motion, which was that on very short times, particles would behave ballistically, right? They would go kind of in one direction until they got enough. I think there's just a button that switches the order. Here, why don't we use, do you want to try my computer? I don't need slides. Okay, so basically what was happening was that you know, in short times, you would just see ballistic motion. Okay? So that was already recognized. And what I'm going to try to explain in the rest of the lecture is another apparent, in my opinion, shortcoming of the theory, which is that it forgets the fact that all of the particles are in the same environment. Right? Like, you know, you have the same background water that's moving all the particles around. So it would make sense that the particles that are near each other, just like, you know, leaves in a stream, will kind of track near each other for some amount of time and then maybe depart from each other. Ah, perfect. So, and that might have some effect. So what we're not going to do is we're not going to try to model every single particle of water and create a sort of full, you know, full model for the entire system, right? That's very hard, as people in this audience know. What we're going to do instead is model the environment in which particles live as being statistically random. But all particles are living in the same statistically random environment. So let me explain. So first of all, the Einstein model would treat, so this is just a, you know, it treats each particle, let's call it particle x1, x2, x3. It says each one evolves as independent Brownian motions. So dB is, or B is a Brownian motion. So what you're seeing is that if you look at the trajectory of three different particles, they look essentially independent of each other. Okay, and this is what Einstein's model would have you believe. Okay, now what the type of model that we're going to be interested in, and I'll focus in a little while on a very specific version of this, and then go back to a general version later, is what's called a random walk in random environment model. And there are different versions of this type of model. And the type that I'm interested in involves a forcing field which varies quickly in both space and time. So you should imagine the following picture. So this is at, say, time 0. And the different colors and the sort of different arrows, these are little arrows if you can believe it. It says that if a particle is at a given location, it will be subject to a force which is dictated by this picture. And if I wait a little bit of time, then I get a new picture of forces. And I wait a little bit more time and I get a new picture. So depending on where my particle is, if I'm at particle xi, I feel the force c at time t and at the position where I currently am. And there's some sort of common noise. So this c is that all particles that are at a similar location at a similar time are going to feel a similar force. Plus each one will have some independent noise that's acting on it. So this is somehow an in-between model. It doesn't allow all the particles to move independent of each other, but it inserts some independence in the form of this Brownian term. But it also couples them to some common noise in the form of this c term. And so what you'll see if you look at the traces of a few particles is that they will actually stick together This is not a simulation. This is me being lazy and just rotating the picture slightly. But anyway, what will happen is they will stick together for some amount of time, and then they will start to spread apart, and then they won't really see each other, and they'll behave independent, and then they'll stick together, and then they'll separate. And again, I should do a better simulation of that, but I didn't. I'll show you a version of it in a moment that's better. So this is, I'm going to now focus on a one-dimensional. Here I was talking about, this is of course a two-dimensional version of the model. And you can imagine this in arbitrary dimensions. But for the purpose of this talk, I want to focus mainly on one dimensions. And this is where the connection to KPZ will be most robust and where we can say the most, though we are interested in doing work on the higher dimensional setting. So, OK, if this doesn't speak to you, this little picture, here's a very concrete model. And this is one that Guillaume Barracon and I introduced about 8 years ago. So the model goes as follows. You imagine that you have a one-dimensional space, so horizontal, and then, of course, one-dimensional time in the vertical direction. I'll eventually learn how to use this pointer. And what happens is that you initially have a bunch of particles that start off. There we go. Okay. That start off at the origin. And depending on the color of that location, they have a certain probability of moving left or right. Okay? So each location has a color. The colors are chosen randomly on the spectrum of blue to red. Blue means left-leaning. Red means right-leaning. There's no political implications of this. I would have preferred an entirely blue picture, though. But oh well. Anyway, so all of the particles here, so most of them will move to the left. So something like 90% of them will move to the left. And OK, so here's an example where I have 5 particles. So we flip a coin. And of course, that doesn't mean that all of them move left, but some larger proportion. And then they end up in a new location at a new time. You should think of these as little kind of segments of a continuous model where I've done some coarse graining. And then you just let them evolve. So here, most of the particles will move to the right, because this is a heavily red region. And you see the space-time randomness in the form of the fact that this is really like a checkerboard in terms of colors. So the question becomes to understand the system as a function of n, the number of particles, and time, the vertical direction. And of course, also as a function of how you choose these biases. So here I've chosen them somehow uniform on the scale of red to blue or blue to red. In fact, we will consider a more general, well, later I'll consider a very general class. But for the moment, I want you to think about what's called the beta distributed law for these biases. So if I'm thinking of, again, the spectrum of blue to red, if I have a beta random variable at each one of these locations, and I have this parameter alpha and beta, I'm going to take them to be equal. If alpha equals beta equals 1, then I have a uniform color between blue and red. As alpha and beta go to 0, I basically end up in a model in which everything is entirely blue or entirely red. Right? Everything spikes around 0 or around 1. And in the other extreme, I have that everything spikes around a half, which would mean that I have an entirely white model. So on the one extreme of this picture, where everything is exactly blue or everything is exactly red, you'll see that all of the particles will just follow the same trajectory. Right? Everyone moves to the left in lockstep. If it's blue, everyone moves to the right if it's perfectly red. So it's in fact it's a system of coalescing random walkers, because if I had started a few particles elsewhere and they eventually join up, they'll stick together. So in some sense, this is like just a one-particle diffusion, where I just look at the trajectory of where this whole cluster goes. On the other extreme, where alpha and beta goes to infinity, the model is white, which means that every particle just chooses 50-50 to go left or right. And this is really the Einstein model. Each particle's trajectory is independent of each other, and they basically behave like random walks. So we're kind of interested in understanding the crossover between this, which is like an n equals 1 version of the Einstein model, and this, which is the n equals n version of the model. So this is a model where the environment couples together the randomness of the particles, but in some particular manner. Yep.
You change the kernel distribution at each time step?
Exactly. Well, we have the same distribution, but at every single space-time location, we draw independently from that distribution. So essentially, another way to think about it is that you use different coins at every space-time location, and they're weighted coins. The other comparison I give is, you know, a Galton board where you have the little nails and then you bounce off of the nails. Imagine that the person making the board was drunk. And so they kind of knock one to the left and one to the right and one to the left and then another to the left. So when the balls are knocking, they don't go 50-50 left and right. Sometimes they go 75-30 or 25 and so on and so forth. OK, so the basic question is, can we distinguish? We have two different models. One is the Einstein model, alpha beta equals infinity. Everything is white, which means that all coins are 50-50 coins. And then there is our model, which we'll take to be the uniform case, alpha equals beta equals 1. So you have this sort of uniform distribution of colors. And the question is, can you tell the difference? Now, of course, you can tell the difference because you see the environment. But if I remove the environment, can you tell the difference? So in other words, if all that you see are the traces of the particles, can you tell the difference? OK, so maybe I should have made it a little bit more fun and not written which one's which. But what you're seeing here is something on the order of 10,000 particles. And each particle is drawn. And of course, you know, you don't see each particle. You see the sort of intensity of particles per space-time location. And if you look at the two pictures, you can kind of tell a difference, right? Like, so in fact, if you do a little bit of smearing out, so if you kind of blur this a little bit, they look exactly the same. And that's because the typical particle in each model just behaves according to essentially a Brownian motion. Or said otherwise, the density of the particles behaves according to the heat equation in both cases. So at the level of the sort of typical particle, the bulk of the system, they are essentially the same. Again, there's a very small scale difference, which is that you can see there are some areas that are slightly more frequented or slightly less frequented than others. But these are on the microscopic level. So in a real physical system, I think it would be impossible to really tell the difference just by looking at that, because physical systems blur out a little. Yeah?
So I guess in this dimension, it's OK, but I guess higher dimensions, these sort of pockets of where you don't really go that many times become bigger. So as the dimension grows, is it harder to answer this question on the slide?
That's a good question. So in higher dimension, you might expect larger pockets that are somehow excluded. And can you see? I think that still they would be locally finite in the sense that if you just smear it out by something that's growing slightly larger than order 1, you won't tell the difference. And in fact, mathematically, you can prove that at the level of the sort of density of the systems under diffusive scaling, they both converge to solutions to stochastic to the standard heat equation. OK, so that's not really going to be a very good physical way of distinguishing the two systems. Now, the thing that is not apparent in these pictures is what are the extreme particles doing? So they're very hard to see, of course. So let's zoom in and look again at the extreme particles. So if we go back to our system, we can ask, where do the, this is some sort of finite cone. Right? The furthest particles can move is 1 to the left at each step. And we can ask, if we start with n particles, how long is it until there are no particles left on the left boundary? Okay. So in the Einstein model, at each time step, what you do is you basically take half of the particles and you move them left. It's not exactly half, right? It's a binomial. But still, it's basically half. And so you expect that the time it takes for you to get basically 1 particle is like log base 2 of n. The number of times you got to split n in half to get 1. Okay? And in fact, what happens is that not only is it this, it's actually really close to this. The fluctuations around this time, they don't grow with n. They stay of order 1. So you are really close to being exactly that time where you peel off. On the other hand, in our model, at each time step, you take a uniformly distributed between 0 and 1 fraction of the particles, and you bring them left. So the time it takes, and this is a simple exercise in law of large numbers. So you're basically taking the product of a bunch of uniforms, and you want to know until how long is it 1 over n, right? Until you've taken a fraction of size 1 over n. And the time that takes is log base e, or natural log of n. So it actually takes less time for there to be no particles on the boundary. And moreover, the scale of the fluctuations on which this lives has variance also of order log of n. So in other words, the time that it takes for the particles to peel off the boundary is much more random in the system on the right than on the left. And that's, of course, because the environment is much more random, right? Here you have two forms of randomness. You have the randomness of the environment and the randomness of the motion in the environment. Here you only have one form, which is this sampling of the particles within the deterministic environment. Now again, I'm going to contend that this is not a very good answer to my question of can you tell the difference, because in a real physical system, there is no notion of the boundary of the system, and you know, saying, oh, well, this is the time it separates and this is the time, that's kind of a meaningless thing from the perspective of a real physical system. So nice mathematical answer, but not really physically meaningful. What is physically meaningful is to look at later times, so times that are longer than order log n, and ask kind of how far to the right or left are the maximal particles, and how does that vary as a function of the environment. In other words, if I run a new system with a new environment and I ask kind of where the rightmost particles are, you know, and I do that every single day for a year, and I ask kind of how much it has varied, that's something that is kind of physically meaningful. That's something that doesn't really refer to the fact that there is this sort of, you know, discreteness of my system. So that's in fact what I'm going to show here. So what this plot is a combination of theoretical results, which I'll explain in the later part of the talk, and numerical results for the model. And so let me kind of break this down. Okay. So first of all, what's shown here, so this top curve, the one labeled Barraquan-Corwin, this is the variance of the maximal location of n particles at time t. Okay, so in other words, I start with 10 to the 10 particles, all at the origin. I run the system in my random environment. I see where at time t, let's say time 1,000, the rightmost particle is, and I record that number. And then I repeat that with a new system, a new environment. I run a new set of particles in that, and I see where the rightmost particle is. And I do that, I keep repeating that. And I ask, how much does that rightmost location vary? And how does that depend on n, and how does it depend on t? Well, here I'm actually fixing n. So how does it depend on t? And so what you see, so that's what this red curve is. The Einstein curve is the one that's labeled here. This is this whatever other color, red or green or purple. So the Einstein model turns on at a time which is of order log n, in fact log base 2 of n. And then there is some sort of steady increase ultimately to a power law in time, which has an exponent of 1 of the variance. So in other words, and this is what you just get from extreme value statistics. If you take independent random walkers and you ask the rightmost location, the Einstein model says that there's a certain power law associated to the location of that rightmost particle, and that's the result of sampling the particles in a deterministic environment. In the presence of the random environment, there's much more randomness in terms of, this is a log-log plot, by the way, in terms of the variance. So the system kind of turns on at a more random time, and it has a lot more randomness in the location of the rightmost particle. And then eventually, as you run to much later times, it kind of coalesces again with the Einstein solution. So what the message here is that there is a sort of transient time during which, what I'll call a medium time or medium density regime, in which the random environment really displays a very different behavior than in the deterministic environment. There's a different power law that's dictating this curve here, and different coefficients and all that sort of jazz. Okay, and I'll tell you what that is a little bit later in the talk, not just give you plots. So at first, this seems like a good thing, right? Like the random environment introduces a different power law, and there's some time scale on which it lives. The time scale is basically between times of log n and times of log n squared. And then eventually, once you go past that, it kind of, the two, you can't really tell the difference. You have the same slope. Now, the only problem with this, again, is that in a real system, a system of, say, 10 to the 10 particles, log of 10 to the 10 is not a big number, right? It's like 30 or something, right? And so, and log squared is not that big. It's like 1,000. So in principle, actually reading off what this curve looks like and distinguishing it from the Einstein curve is going to be really hard for any realistic system size because you're taking logarithms. Okay? So this is a bit of a ghost. The fact that these two curves are different is a bit of a ghost because it only lives until some scale on which we're really interested in long time behavior. And so all is not lost, though, because the following is true. If I look at our curve, so our curve accommodates both the randomness of the environment and the randomness from sampling, and I subtract the variance of our maximal location from the variance of the model under the Einstein, or the Einstein model, then you see that there is actually a different power law. The difference between these two variances, which somehow corresponds to the variance due to the environment, right? The Einstein model is purely about sampling. Ours has the environmental randomness and the sampling randomness. If you take the difference of these two curves, you actually recover a power law with a smaller exponent, a slope 1/2, and a coefficient which can be read off from it. And that coefficient is what we call the extreme diffusion coefficient. And this power law persists basically arbitrarily far in time. It's something that you can actually read off. Okay, so the point here, the sort of punchline of this picture is that even though in terms of their sort of absolute curves, it's hard to distinguish once you go to a relatively long time, if you take the difference of these two curves, you get something that holds true for all times, essentially, and in fact holds true to relatively small values of n. This picture is for 10 to the 7 particles, which is a fairly small system size. And in fact, if you just take something like 100 particles, 10 to the 2 particles, you end up with a picture that looks similar to this. So you can actually pick out this coefficient and this power law without needing too many particles. So there is really some effect of the environment that can be read off, and that can be read off over many decades of the system. Okay. So what? So what I want, this is the result of numerical experiments and some mathematical work. But what we'd really like to do is be able to read this off in a real physical system. In particular, read off the power law and read off the shift, the coefficient corresponding to it. And I'd like to tell you, and I'll tell you a little later, what the meaning, the physical meaning is of the coefficient of this power law. It has a very nice microscopic physical meaning. So we're not just doing theory. My brother is an experimental physicist, and I convinced him to do some experiments. And apparently experiments take a while, so they're still in progress. Let me give you the sort of schematic for the first experiment, and then I'll show you what it actually looks like. You should imagine, and this is how I imagined it, and then the picture looks nothing like this. But imagine a long, thin tube, okay? And you start with lots of particles all the way at the left of the tube. And you, on the right, have a little microscope. And the particles diffuse. So there's some sort of media in this picture. Maybe it's some glycerin and water or mixture. And the particles just slowly diffuse. And what you can do is you can either measure the location as a function of time, and that's the plot I was giving you before, or there's a sort of dual measurement, which is I measure the first passage time past a given location. And maybe I vary that location, and I kind of build up a curve as a function of the number of, or the location of where I put the microscope. And our theory also applies in that setting. It's a slightly different picture, but it's very similar. And so you repeat this experiment lots of times, and you build up a histogram and you try to understand that in the relation to our theory and kind of understand the effect of changing the number of particles and changing the location of the microscope, and of course changing the nature of the particles and the media in which they live. This is what the actual experiment looks like. Yeah, nothing like what I imagined. But so what he did is he put these little, basically like needle capillaries on a some sort of rotating disk, which you can centrifuge. So it spins really fast. It forces all the particles to the exterior. You have something like 10 to the 10 particles, 10 to the 12 particles, and then you have a good microscope with a fancy name. I don't remember the name. That measures where the particles are as a function of time. And in fact, because these are such thin capillaries and the particles are so small and the media is so viscous, it takes something like a day for the particles to go from the outside to the inside. It's like a few centimeters, but it takes a long time. And you can repeat this, and you can kind of build up your histogram in this way. And this is what they're doing. And as you can imagine, it takes a while to get enough information for this. But the idea will be to try to test whether the theory is somehow indicative of what the reality is. And moreover, yeah.
Sorry, how do you realize the random environment?
You do nothing, right? The random environment is just, you have an environment, right? There is randomness inherent in the environment. There's thermal fluctuations of the environment. There's little eddies within the environment, right?
Right blue environment. Right blue, red blue environment. That's in the model.
So the red-blue environment is supposed to be a model for, and sorry, I should make this clear. It's a statistical model for a real environment. So a real environment, of course, is much more complex. But the belief is that you can effectively model the environment through some sort of quickly mixing random field. Now, of course, that might be a completely wrong assumption, but it's somehow a little bit better than Einstein's, which would say that you can model the environment as each particle being independent of each other. And so the question will be, is this a good model? And the only way that we'll tell it is by actually doing experiments.
Yeah, so kind of as a follow-up for the red-blue model, do you know what happens if you add some correlations between the layers? Because maybe in practice, especially in the kind of fluid case, right? There's not, the fluid has its own way of moving, and somehow you're not just picking a random thing every time. Do you know if this curve persists?
So you should really think of the red-blue model as already somehow coarse graining a system in which there is some correlation. Now, so really what's happening is, first of all, we should assume that the environment is mixing faster than the particles are moving. And that's certainly true in this context. Okay, the thermal fluctuations are varying much faster than the day on which it takes the particle to move through the system. And then what you should imagine is that there is somehow some sort of space-time coarse graining that's going on, so that you kind of look at far enough in space and time that you can treat things as independent at disjoint. Now, of course, the scale on which you do that is important. And so one of the challenges in relating this to the model is somehow understanding what is the right coarse graining, what is the right size of the sort of parcel in the coarse graining that you're going to do in order to make them match. Of course, the picture will be very different if the environment is constant in time. So to be clear, that's kind of a very different type of model than this one. The other type of experiment that's being run, and this one actually we have more data on, and it's probably not the right system to test our theory, as we've realized, but still it's interesting. Actually, what's interesting is that, to our knowledge, nobody has ever actually studied the extreme particles of large diffusive systems. Okay. We've found nothing in experimental literature on that. But this is a photonics experiment. You can do it in 1, 2, or 3 dimensions. So, for instance, let's say in 2 dimensions, you could say take a disk and you shine a laser, a very high concentration, short femtosecond laser. It pumps in something like 10 to the 17 photons. And then you have a disk that is filled with some sort of disordered media. It could be like, little beads, very, very small reflective beads that are kind of jiggling around in water or something of that sort. And you have photosensors on the outside, and you measure how long it takes any photons to escape the boundary of the system. So you should imagine that the top and the bottom are somehow covered in a reflective, a mirror. And so that they bounce around wildly, and eventually some of them escape. Of course, some get absorbed. And what we've found so far is that actually photons are really fast, and they don't scatter that much, the ones that escape. So actually, there are probably not enough scatterers to really feel the randomness of the environment. So this is probably not well described by our theory. At least that's the sense I got. So I think that the first type of model is going to be much more effective in terms of testing our theory than this one. But there still is interesting stuff that's going on here that we've been looking at. Ultimately, the sort of goal here is to build up a table. Okay, so much in the way that once you have this Einstein theory of diffusion, you build up a table of diffusion coefficients, right? Diffusion coefficients for each pair of media and particles diffusing in the media. You can compute a number. What you would hope is to build up a coefficient for the extreme diffusion, a table for extreme diffusion coefficients. And the hope would be that this will tell you something about the system that might not be present in understanding this coefficient. So for instance, and here's kind of the ultimate test, is to make a differential measurement. What you do is you choose two types of media particle pairs that have the same bulk behavior. In other words, they have the same Einstein diffusion coefficient, but that have very different microscopic behavior. So for instance, you could imagine taking what's called a Newtonian fluid, so something like water and glycerin, versus a non-Newtonian fluid, a polymer melt, things with very long correlations and long strands. You can tune, by changing the proportion of water and glycerin, you can tune them to have the same Einstein diffusion coefficient. But they still are microscopically very different systems. And so what you would do is you would tune them correctly, and then you would make the differential measurement of looking at their extremes. And you would ask, how do the extremes look? How different are the extremes? In principle, if our theory is correct, the extremes should display at least different coefficients, but the same power law, but different coefficients. And that would read off something that would be telling you the difference of these two systems in a serious way. Of course, what you really would like to do is kind of turn this around and use our understanding then of extreme diffusion to be a microscope into the hidden world in which the diffusion is occurring, right? If you can look at extreme particles, the particles that are kind of going the furthest, and infer something about the hidden microscopic nature of the environment, that could be very powerful. You could imagine using that in many different applications. Of course, that's kind of many iterations away from what I'm telling you. OK, so this is somehow the end of the physical phenomenological part of the talk. Okay, and what I'm going to do now is I'm going to transition to a more mathematical explanation or treatment of this subject, and kind of cycle back, and we'll kind of eventually come back to that plot that I gave you, and we'll unfold what it means in a more precise way. All right, before that, any questions about this sort of first half of the talk? Yeah.
So in terms of the experiments, you're really probing this variance of the environment minus variance of the sample, right? Because I guess naively you could test your theory by having a microscope at earlier times to try and get this difference between the curves, right? That's harder, right?
That's right. So you could, OK, so indeed what the theory looks at is it looks at the variance of the maximal particle in the random environment, which somehow has two components. It has the randomness of the environment, and then the randomness of sampling in the environment. And what we're seeing is that if you subtract off the randomness due to sampling, which is the Einstein model, we're left with something that has a nice power law, which is different, and a coefficient. Now, what you're saying is, why do that? Why not just look very microscopically at the system and try to observe what's going on at a very microscopic level? And I think that's a good idea, right? Like, there's no problem with doing that. This is a different, it's a kind of a different scale on this. And there are some reasons and some contexts in which you couldn't do that. For For example, one method that's used in breast cancer detection is to shine light through the breast tissue. And of course, they're not using this theory, but there is study on kind of how much light makes its way through and how that depends on the different type of material in which it's being shined through. So that's an example where you can't do a microscopic probe. Photons are moving too fast. You would need to go inside of the breast. But you can kind of probe the response and what's coming out. So there are instances where you don't have that capacity.
For the examples of photons, you consider possibility of interference of waves?
No. So that one I ultimately think it's too quantum, there's too much quantum and it moves too fast. There's not enough scattering. In the end, I don't think it's a good model. I don't think ours is a good model for describing that. But even in the classical system, in the particle diffusing system, we're also not taking into account the fact that particles, knock into each other. And that also can create some additional effects. We are looking at very diffuse systems. Even though there are 10 to the 10 particles, that's relatively diffuse compared to the number of, the size of the system.
In the previous plots, I guess you were plotting empirical variances, and you say like there is a nice parallel when you do subtraction between the variance of your method and Einstein's model. But actually, it seems that on large scales, on large times, you have bigger oscillations. Is it due to like neither order effect of fluctuations compared to the background of the dynamics?
So the question, this yellow-orange curve is exactly this variance of the maximum minus variance of the sampling. And indeed, it's not a perfect, it's not perfectly tracking, right? It's kind of bouncing around a little bit. This has to do with the number of samples that we took. That's part of it. And also the finite, the fact that n is relatively small. If you take n as 100, you see a fair amount more bouncing around. If you take n as 10 to the 10, it's much tighter. So I think 10 to the 10 is probably a good one. Yeah. For the time at which the leftmost particle separates from the boundary. Well, so in the model, it's a very well-defined thing, right? Like you have here I've kind of rotated time so it's horizontal. You can ask exactly at what time there are no particles on the left boundary or the upper boundary. That's some number, right? It depends, of course, it's random. So you can ask like a law of large numbers. As you take n to infinity and you divide through by that time by the right, say log n, what number do you get? So in one case you get like 1 over log 2, and in the other case you get 1 over log e. So there's a different kind of general time at which you separate. But again, this is kind of not the right thing to look at from a physical perspective because, this is not a real model. It's a model, but it's not a real system, right? Like this is not reality. There was another question. Yeah.
I might have missed it, but so the max Tn is the variance in the most extreme position for your model, right?
Yeah, I haven't defined everything, and I will later. But so max Tn you should think of as a random variable that depends on the environment and a sampling of particles in the environment. And it's the location then of the maximal particle. So you all start at the origin. It's the particle, it's the location, the rightmost location that has a particle.
Right. And it's the same thing true for the SAM, just without the...
So, no, so in fact, there's a little bit of subtlety in defining what this SAM and T is. And the way I really think about it in this picture is that it's just the thing that you get if you do the Einstein model. It's exactly so this variance of SAM is like the thing that you have in the Einstein model. And that's the thing that you should subtract off. In reality, what I'm going to do is the following. I'm going to define something in a little while, which is called nth environment, NT. And that is the location at which the tail probability, given an environment of the transition probability of a random walk in that environment is 1 over n. It's like the 1 over nth quantile of the random transition density for the system. Random because the environment was random. That is something well defined. SAM is going to be the difference between the maximum and that location. So it's how much you vary around that sort of, given the environment where you kind of expect your maximum will be. And that will define the SAM NT. And in fact, what we'll show is that these are essentially independent. Once you know where the 1 over nth quantile is, it doesn't really tell you much about where you're going to fluctuate around that. But I'll come to that. I'm going to be a little more precise in a moment. OK. I'm going to go on. If there are more questions, please stop me, because otherwise you won't have a chance. OK. So what I want to discuss now is why where does this picture come from and what can we do? OK. This is a bad joke I made the first time I gave this talk, which is that I want to explain why. So I said a bridge over the river Wye. There's this river Kwai, right? Like this famous movie. This is the river, the bridge. And in fact, when I gave the talk the first time, I was in Bristol. And somebody told me that Bristol's right here. Somebody told me that there's actually a river called Wye right next to where I was. It's spelled differently. And that maybe my joke would have been funnier if I had realized that. Now, I couldn't think of a funny joke about the river Yvette, I guess, is what I'm near. But anyway, I apologize about that. So, OK. So why can we say anything about this? And in fact, how did we come upon this picture? And the story is not that I was interested in this many particle diffusion. In fact, that was kind of an afterthought. What we were interested in and what I work in is an area called integrable probability. And it's an area in which you try to bridge certain algebraic structures and symmetries and certain probabilistic models and asymptotic phenomena. Ultimately, this bridge is kind of only true for very specific models. But what you bring by going across the bridge is that you're able to show that both sides well, at least in terms of some universality results, you're able to understand or predict what the behavior of a much larger class of models should be. And this is the sort of KPZ universality class. So I want to give a little bit of this picture. And of course, you'll get more of this picture over the course of my other 2 lectures. But this is kind of the general mathematical point that I'll try to get across in some of these talks. OK. But before going in that direction and telling you kind of what is the integrable structure here, I want to back up, in a sense, to the beginning. And I want to rederive, the results of Einstein and the curves that I'm talking about. I want to explain at kind of a more mathematical level. OK, so the Einstein model, again, was the one in which you went left and right 50-50. Or, if you want to kind of take the parameters alpha, beta from my beta distribution, you go, some bias left or bias right. You can forget about the alpha and beta. Just take it to be a half left and a half right. So every particle goes 50-50 left and right. Every particle is independent of each other. And that's great. So in probability, there are 3 kind of things that you do, at least that you initially do. And then, of course, you can do more. You prove a law of large numbers, a central limit theorem, and a large deviation principle. So what a law of large numbers tells you, and I'm sure this is familiar to all, is that if you look at the trajectory of a single particle and you divide it by time, so you look at the sort of empirical velocity of the particle, it will converge in various senses to the expected jump of a single particle. So in this case, if alpha and beta are equal, it's 0. Okay, so at the speed t, you basically just go straight up. If you zoom in with both directions, like t, what you see is essentially vertical. And of course, that's not exactly true. There are some fluctuations. And if you center by that asymptotic speed, and you scale by the correct constant times square root of t, and this constant is easily read off in terms of, again, the microscopic jump, you converge in distribution to a normal 0, 1. Said otherwise, if I look at the density of the particles at the top of this picture, it's going to be approximated by a Gaussian distribution, which bell curve distribution with width sigma times square root of t. Now the large deviation principle, the first time that you see such a thing, you kind of think, who cares? So the large deviation principle says that if I ask the probability that my particle goes much faster, let's imagine that little x is something that's bigger than this law of large numbers speed. If I ask the probability that I go much faster at a different velocity than that, this will decay exponentially. So if I take its logarithm and divide by t, I'll converge to a negative number, minus I x, x of course being the speed at which I'm going. And this I has some nice formula. In the case of the independent identically distributed jumps, it's written in terms of this Legendre transform of the cumulant generating function, which in the case of the 50-50 Einstein, left-right simple symmetric random walk, has this nice form in terms of logarithm, this entropy function. OK, why do you care about large deviation principles? So for me, the reason I care about a large deviation principle, I best illustrate in terms of turning on my car in the morning. Okay, so every morning when I go to work, I turn on my car. Okay, now if the chance that my car explodes is 1 out of a million, it doesn't faze me that much. I can kind of accept that risk, right? If I turn on my car and I have a 1 out of a million chance that it explodes. But from the perspective of the country or the world, every day millions, say 100 million people are turning on their car. So that would mean that every day 100 people die from their car exploding. So large deviations matter when you have lots of independent instances of something, and you want to know whether or not something really bad happens. Okay? Of course, that's not where the theory started. It started off in the theory of insurance. But where you see that this matters is if I look at the behavior of many particles, and I ask what's the probability that the maximum of those n independent particles, so the superscript is I'm labeling the particles, the subscript is time, and I ask the probability that the maximum is less than or equal to some x, you see that that can be written by independence and the sort of tail probability formula as 1 minus the probability that a single particle exceeds little x to the nth power. And so if I want to know where, if n is a really large number, if I want to know where this maximum is roughly, I should find the little x so that this tail probability, the probability I'm bigger than it, is roughly 1 over n. Right? Because if I do that, then the right-hand side will look like 1 minus 1 over n to the n, which is something like e to the minus 1. It's some number between 0 and 1. It will give me a location where my probability transitions from being 0 to 1. Okay? So that's why this 1 over nth quantile, this area where the tail probability is like 1 over n, is going to be important. And this, of course, this formula is important. So what you learn from this is that if you're interested in large n, in knowing kind of the fluctuations of this maximum, what you really need to do is understand, well, either the large deviations, or as n grows, eventually you move kind of, as time grows, you move in the direction of the central limit theorem. So if I kind of take n to be large, and as time varies between time of order log n and longer, I kind of, in this formula, in order to find the 1 over nth quantile, I need to go and I need to study the large deviations. And then as time progresses, I actually need to probe what's called the moderate deviations, which is where I'm asking for probabilities that I'm moving not exactly at a faster velocity, but something that's kind of intermediate between square root of t and t. And so these moderate deviations that somehow transitions between large deviations and central limit theorem will be important for understanding this maximal behavior. OK, so this is the Einstein model. And from this, you were able to prove the curve and deduce the power law and compute the coefficient in terms of the Einstein diffusion coefficient and all of that. OK, what about our model? So first of all, let me be a little bit more mathematically precise about what our model is. So our model has an environment, which I take to be, I'm going to use the symbol capital B sub Tx. So each one of these is the bias. B is for bias. And I'm taking them IID and according to some common distribution that's supported on 0, 1. Okay, you can take it to be the uniform if you want in your mind. And that's what's shown in this picture here. The probability measure on the environment, I'm going to use this boldface P to represent. Okay, so this represents the randomness of the environment. So I choose my random environment according to this law, boldface P. If I am given an environment B, I'm going to let this sans serif P sub B represent the probability measure of random walks, so many random walks potentially, given that environment. So given the picture here, this you should think of as one instance of the environment. Now I can sample a random walk in that environment. And the way I sample it is if my random walk is at position x at time t, I go and I increase with probability btx, and I decrease by 1 with probability 1 minus btx. This is just the biased coin that I'm using. Okay? So the question is, again, what happens? And I want to describe the law of large numbers and central limit theorem. And then we'll go to the large deviations. So it turns out, and this is, of course, amazing, but it also is justifying the fact that you can't really tell the difference in terms of the bulk behavior of the RWRE model and the Einstein model. It turns out that for almost every instance of the environment, so if I sample an environment according to this law, boldface P, and then I look at the trajectory of x of t given that environment, that will satisfy the same law of large numbers and central limit theorem as in the presence of the averaged environment. So in other words, if I replace all of these B's by their average, so in this case just by the Einstein, by everything being white, and I look at the trajectory of a single particle in the either quenched or the averaged environment, they will look statistically the same. They will both converge to have velocity 0, and they will both satisfy a functional central limit theorem where they'll converge to the same Brownian motion in law. So that is why you can't tell the difference in terms of the pictures of the bulk or the pictures of a typical particle. You can't tell the difference between the two models. And that's because of this result. Okay. Now, again, this is for almost every environment. So, of course, you can create environments for which it's not true, but that is of measure 0 relative to the law on the environment. Now, moreover, you can show, and this is shown in these works, you can show that the random environment model also satisfies a large deviation principle. So if I look at given an environment B, sampled according to this law, boldface P, if I ask the probability that I go faster than velocity little x, that will decay. So I take the log, I divide by t, I put a minus sign. It will converge to a constant, I of x. And this is a constant that is actually it's not random. Okay? So the large deviation rate is not random. But the dependence of that rate on the law of the environment is completely inexplicit. Okay? So good luck finding a formula as simple as this 1 plus x log of 1 plus, this entropy formula in the presence of the Einstein model. Okay? And moreover, I should say another shortcoming of this result is that the left-hand side is random prior to taking t to infinity. Yep?
So this is again for almost every environment?
This is for almost every environment. You will converge to the same thing. Of course, you can cook up an environment of measure 0 for which you converge to something different. The left-hand side before you take the limit is random. And the randomness of that is, of course, of smaller scale than t. Right? It's being washed out. But it's exactly that randomness which is the environment's effect. So when we're interested in the effect of the environment on the rightmost location of particles, that's the thing that gets lost in this limit. Okay? So what we'd like to know is we'd first like to know something about the right-hand side, and then we'd like to know something about what was lost when we took this limit and brutally divided by t. And so this is where the integrability comes in our ability to say something very precise. So Okay, I guess I never defined what it means to be beta distributed, so let me remind you or tell you. A beta random variable has a law supported on 0, 1, and the density of it is proportional to y to the alpha minus 1, 1 minus y to the beta minus 1. That's some gamma normalization. These are the plots I gave you from before. Of course, you see if alpha and beta are 1, you just get 1 and minus 1, so you get 0 and then 0. So this just gives you a constant, which is why you get uniform. So this was the model that we're studying, and I'm going to give you the result only in the special alpha equals beta equals 1 case, though we are able to do this for all values of alpha and beta. If you take the left-hand side, still this object, you take the limit. This is this rate function that is completely inexplicit in general. It turns out in the presence of this of the beta environment, this special choice of environment, it has a very simple rate function. In fact, much simpler rate function than even the simple symmetric random walk does. It's 1 minus the square root of 1 minus x squared. Okay, this came as a complete shock that there was such a simple formula for this model. And moreover, and this is now bringing us in the direction of KPZ, if I look at this quantity, so this is the tail probability given the environment B, I took its logarithm, I add back in the thing that it's kind of behaving like, I of x times t, and I ask how much is left behind in terms of the effect of the environment. So I do this for one environment, I get a number. I do it for the next environment, I get a number. And I do this maybe 1,000 times. I build up a histogram. That histogram will live on a scale of order t to the 1/3 with a coefficient that is explicit. And if I look at the limit as t goes to infinity of that histogram, it converges to something called the Tracy-Whittem GUE distribution that I think Kazumasa probably spoke about in the previous lecture. Okay? So in other words, the randomness due to the environment is exactly, in this large deviation scale, is exactly given by this Tracy-Whittem GUE distribution, scaled by this function sigma x. Okay. So what does this tell us in terms of the picture from the first part of the talk? So first of all, let me tell you now what I meant by this mth nt. This is, I look at the location of the 1/nth quantile, right? It's somehow if you remember this formula for the maximum, right? It's like the maximum of a bunch of independent stuff is 1 minus the tail probability to the nth power. So I kind of ought to look at the location where that tail probability is 1/n. But of course, this is a random variable now because it depends on the choice of environment. So I ask, how random is this environmental location? Is this 1/nth quantile? How much does it vary? And that's what this mth nt is. And so what the curve, so what this blue curve is it's exactly the result of computing from the result I just gave you, computing what this variance of this environmental term is. That's this kind of dotted blue curve is. Now the scale in which the result of large deviation applies, it actually turns out that it applies in what's called this medium density or medium time regime. So it is, if I want to kind of reverse the picture and study not as n goes to infinity, but as t goes to infinity for fixed n, there's a sort of a balancing act that goes on. And as I said before, as t progresses, you move from large deviations to depending on moderate deviations. And so the large deviation regime is really this regime between time of order log n and time of order log n squared. And so the curve in this region, this first or this middle region, is exactly corresponding to the result that I showed you. So it's really nice, but as I explained to you before, somehow from a physical perspective, it's actually not the most interesting regime because it's too transient. The time between being of order log n and log n squared is too short to really gain too much information. So what actually is physically more interesting is understanding what happens when you go past that time. And that's what I want to tell you now. Okay. Just before doing that, I just want to say, if you look at the behavior for different environments, so not the beta environment, it will give you different curves. Each environment will give you a slightly different curve in this region. And in fact, we don't know how to describe the curve. So there's the behavior in this medium density, medium time region is a little bit tricky because we know how to do it for a special model, but we don't know how to do it for general models. It turns out that for general models, we know how to do everything in this more interesting, more important long time regime. And that's what I'm going to explain. So somehow physically, in fact, this result I just showed you is not the most interesting. What I'm going to show you right now is arguably more interesting. OK, so what is being plotted up here is I'm looking at 3 different choices of environment. So one model is the beta environment with the uniform, alpha equals beta equals 1. That's the red curve here. And then I choose 2 other environments. So that the red curve is uniform. You see, this is the density of the red curve. The yellowish orange curve is some other density that is somehow plotted here. It's some weird looking quadratic type thing. And then the blue curve is hard to read off, but it basically puts a delta mass, I think, of some height at 1/2, and a delta mass of some height at 0, and a delta mass of some height at 1. The point of this is that I've tuned these 3 distributions to have the same mean, so they're all mean 0, and the same variance. They're all whatever the variance of a uniform is, like 1/3 or 1/6 or whatever that number is. And that what's being plotted here is the variance of due to the environment. So the analog of this blue curve, right? This thing that we're interested in. The thing that's really picking up this interesting power law. And what you see is that, look, the quadratic and the beta, the densities look pretty similar to each other, kind of similar. And in fact, the curves look pretty similar to each other. And maybe that's not so surprising, right? There's some sort of perturbation. The delta environment, this weird one where there's like some probability that everyone is blue, and some probability everyone is red, and some probability that you're just white. That one is really weird. So the variance increases, and then at some point it actually decreases as a function of time. You're kind of less sure of yourself, and then you become more sure of yourself. It's a weird nonlinear effect. And then eventually they all kind of coalesce. And so what you're seeing is exactly this. So in the medium time regime, there is non-universality of these curves. When you move to the long time regime, the curves become the same. And they follow the same power law. And that's because of the following theorem. So this theorem, and I'm going to actually build up a more general version of this theorem, but let me start with the simplest one. So I'm considering models in which I go left or right with some probability, btx, right? And I've tuned it so that so the b's are centered, so they have 50-50 probability of going left or right. So that's the mean is 1/2. And I've chosen the variance to be fixed, something sigma, 4 times the variance to be something called sigma squared here. If I consider any distribution with the same mean and the same variance, and I look at the tail probability that you are at time LT to the right of L to the 3/4 t plus some smaller deviation of L to the 1/2 t, then this random variable multiplied by some deterministic coefficient depending on L, t, and x, and not on anything else about the distribution, converges in distribution, not just for fixed t and x, but actually as a process in t and x, to the solution to the multiplicative noise stochastic heat equation, which we know or we'll see from Casamaza is related to the KPZ equation by taking logarithms. And the only thing that impacts this is that the coefficient in front of the noise term, so this is space-time white noise, and this is a multiplicative term. The coefficient of the noise depends on this sigma squared. In a very simple way, square root of sigma squared over 1 minus sigma squared. So in other words, if I probe the moderate deviations in this L to the 3/4 scale, which is somehow corresponding to the transition away from this medium to the long time scale in this picture, then I get something that's universal. I have a universal scaling limit, and by using this sort of maximum in related to the tail probability stuff, I'm able to relate this to the behavior of this curve. And that gives me the curve, and that tells me not only the power law of the curve, but it gives me the coefficient. And it relates the coefficient to this sigma squared. So that's what gives us the long time behavior in this curve. And that's what gives us the power law. It has to do with the, so in fact, there's a sort of negation of time. If you look at the long time behavior of this model, it's like taking the short time behavior of the stochastic heat equation or the KPZ equation. And so really, you're kind of moving into the Edwards-Wilkinson class. I want to present a more general version of this result. This result you see is just the nearest neighbor model, left, right. But as was rightly asked, you could deal with much, much more general types of models. And I want to tell you just a bit about how you do that or what that might mean. So, OK, so first of all, we saw that the limiting coefficient in this KPZ or stochastic heat equation is what dictates the diffusion, this extreme diffusion coefficient. I haven't gone through the details of that. But somehow the discrete model of going left and right by plus or minus 1, it doesn't tell us really what that coefficient means physically. There's kind of not enough space to really see what it means. So that's what I want to flesh out here in this much more general example. So here's the picture. This looks complicated, but let me just explain what I mean. I choose a common distribution at each space-time location of the jump distribution that particles will see there. So in other words, and just this is the example you should have in mind. Consider a Dirichlet distribution, say with parameter alpha, 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 alpha. So a Dirichlet distribution gives me a collection, in this case, of 5 numbers, non-negative numbers that add up to 1. It's a random point in that simplex of numbers that add up to 1. Dirichlet is basically the generalization of beta. So it's like the density is 1 minus x1, or it's like x1 to the alpha 1 minus 1, x2 to the alpha 2 minus 1, up to x5 to the alpha 5 minus 1, and then indicator that the sum is 1. And then you kind of look at the distribution that you get on that simplex. Okay? So in other words, choose some collection of random numbers that are between 0 and 1 that add to 1. Call these the x's. In this picture, these x's are represented by these red lines. So at each space-time location, time in the vertical, space in the horizontal, I have a random set of red lines. But they're chosen according to the same distribution. Okay. What the black curve, or the black line represents here is, at each location, what is the mean of that distribution. Okay, so if I have a lot of, you see a certain location has a very thick red arrow moving to the left, then the mean will probably point in that direction. And the mean, of course, is kind of wild. So you should think of the mean as like the bias due to the environment that's felt at each location. And then the red is kind of like how much randomness there is around that bias. OK, and as before, we're going to run many, many particles in the same environment. So you start a bunch of particles here. You let them evolve according to the distributions given by these red arrows. And you see what happens. Okay. And this is, of course, this is just, again, one example of, we can deal with even more general types of models. But this is one example. OK, so first of all, we show that if you look at the variance of the maximal location of a particle at time t, it's essentially the sum of the variance due to the environment. There's this sort of 1 over nth quantile variance under the random transition probability, heat kernel, plus the variance due to the sampling, which is like the sort of Einstein behavior, and you can compute what the asymptotic behavior of this variance due to sampling is. I'm assuming I'm now in the long time regime, where time is bigger than log n squared. The variance due to sampling grows with a linear power law, and that was what I had indicated earlier with this linear slope 1. So it grows like d, where d is the Einstein diffusion coefficient in the averaged environment. So in other words, I replace the environment by the average of each of one of these Dirichlets, so everything becomes sort of deterministic. And I compute just what would the behavior for a single random walker. What's that diffusion coefficient? And this is the formula for the variance due to sampling. Now here's where things get very interesting. The variance due to the environment grows, as I indicated before, with a power law which is of order t to the 1/2, with a coefficient that depends both on the Einstein diffusion coefficient, d, but also on something new, this lambda x extreme, where lambda x takes a very nice form. So it is equal to the ratio of what we call the extreme diffusion coefficient divided by the Einstein diffusion coefficient minus the extreme diffusion coefficient. And what is this extreme diffusion coefficient? It is the variance of the black arrows in the ensemble. Okay? So this is, in a sense, the punchline, which is that that coefficient in the extreme behavior of the system is entirely determined by the Einstein diffusion coefficient and how randomly the environment is kind of on the average steering particles. So these black arrows are, they're rapidly varying. In certain locations you're being pushed this way, others here, like this. So how much that's varying in space and time is can be exactly read off from understanding the maximal particle. That's why when I say that this could be a microscope, that's exactly what I mean, which is that if you can study the extremes, which is something maybe more possible, this tells you what is the effective variance of these microscopic drifts. And that's a microscopic measurement. Okay? So I think that there is something to this that needs to be probed more, but I think this already is revealing something very interesting. And this is what we call the extreme diffusion coefficient. OK, so I have little time left. And I want to give you just one flavor. OK, here's kind of some plots showing that everything works. I want to give you a flavor of how you do this. And of course, I could also do this in the context of the medium time. But let me explain about how do you prove this result that I'm advertising here. Where does this coefficient come from, and where do you get the convergence to KPZ? And I'll be fairly brief about this, but OK. So the idea really goes back in many ways to work of Kardar from quite some time ago now, which is the use of the replica method. OK, so I'm going to explain the ideas of replica. So first of all, in the context of the KPZ or stochastic heat equation, you see that this admits a Feynman-Katz representation. You take the generator here of the Brownian motion, so you're taking a sample path which is Brownian, and you're running it through an environment which is given by this potential Xi, sampled according to that Brownian motion, and you kind of average over all Brownian motions. So this curly E is the Brownian average, and this is some sort of renormalized version of an exponential. But in any case, this defines for you a way to make sense of this ZTX. And if you exchange the Brownian expectation with the disordered expectation, which I'll use this boldface E, this is the average with respect to the environment Xi, you can bring that bold-faced E inside, and what you end up, because you're dealing with a space-time white noise, and you're taking a sort of moment-generating function of space-time white noise, you see that it's only when the Brownian motions, if I've replicated k Brownian motions, so I've written each of these in terms of an independent Brownian motion with this formula, you see that it's only when they intersect at the same time in the same location that you get a contribution to this formula. And so ultimately, this kth moment is written in terms of the expected value over k independent Brownian motions of the exponential of their pairwise local time. Okay, so this measures how much time each pair of Brownian motions spends together. Okay, you need to do a little bit of work to make sense of that mathematically, but this is kind of, at least heuristically, what this formula is saying. So this is an important formula. It allows you to do quite a lot and to infer quite a lot. Of course, if k is 2, this is just the local time of 2 Brownian motions, which is some sort of Levy 1/2 type process. So what does this have to do with the theorem that I gave you? this is kind of going to be a target for us. Now, if we look at the random walk in random environment, I'm going to look at this, the tail probability. In other words, I think I'm changing notation slightly. So I'm going to let R of S be a random walk given an environment C. So maybe I should have used my capital B from before, but whatever. And I'm looking at the probability that my random walk in that environment given by C ends up at location xi at time t. And I'm going to be interested in taking the product over k different locations, or possibly the same locations, xi, and then taking the average with respect to the environment. So this bold-faced E is the environment average. So this you should think of as completely analogous to taking the expected value of the heat kernel of the solution of the stochastic heat equation with respect to the environment. Now when k equals 1, you can just interchange the expected value. So this is like the probability that a random walk ends up in a location. This is the environment. You can interchange the expected value of the random walk with that of the environment. And you see that this is just equal to the expected value that the averaged random walk, so this is the random walk using the average transition kernel, ends up at location x. Okay, so this is like the k equals 1 version of the replica, but this is almost a triviality. It's because, you know, you're taking the product of a bunch of stuff that's independent. You can take the expectation inside. Everything becomes its average. Well, let me show you what happens when k equals 2. So when k equals 2, the random walks, when they're separate, they use different parts of the environment. And so the contribution to the expected value of these sort of tail probabilities, if I look at the probability that one random walk ends up at a location versus another random walk ends up at a location, I can, again, represent each one of these in terms of a sample of a random walk and a sample of an independent random walk given the same environment. And it's only when the two random walkers are at the same location at the same time that the common environment really matters. So I end up being able to represent this as the probability of two coupled random walks, which are basically independent except when they're at the same location, and then they use some joint transition probability. And this is somehow analogous, this is going to end up being analogous to the local time calculation. Okay, so there's a little bit of work that's then done. There's some, you know, I want to show that this sort of pair local time, or this pair expectation ends up converging to the Brownian thing. And there's quite a lot of work, in fact, that goes into this. I need to do some exponential tilting to converge to the Gaussian heat kernel, and some pair local time calculation. But ultimately, well, okay, I probably won't get to do all of this. But there is some calculation of, well, let me just say in words what's happening, because I know I'm at over time now. This expression that you get left with here, you want to show that this somehow converges to the expected value of some exponential of a local time. And what you basically need to do is you need to look at the local time of this random walk, which has some stickiness at the origin, and show that the local time of a random walk converges to the local time of a Brownian motion, and compute the coefficient by which it does. And that takes some work. You use some Tanaka type formula and some martingale decompositions. And ultimately, in the end, that's where the formula comes from through the analysis of this. So I won't go any further, but I hope I've given you a flavor of where KPZ is coming into this picture. And this is a different face of KPZ than maybe interfaces. Of course, in the next two lectures, I'll turn back to talk about interfaces. And hopefully, I've convinced you that when it comes to many particle diffusion, and prepare yourself for a really bad joke, there's more to it than meets the eye, Einstein. OK, I'm done. Thank you.
Are there questions or comments? Just to
clarify, so at some point you start with theta lower, but then you say it's, I mean, the asymptotic result, it's only depend on the variance, it's not sure.
That's right. So the beta result was restricted to what happens in the sort of short time, or sorry, not short time, the moderate time. So if I really want to understand the behavior in this medium time regime, I know how to compute exactly what the curve is in the context of the beta environment. For other environments, I don't know how to compute that, and I don't, and so that's limiting me. But physically, the more interesting thing is this long time regime. That's where you can compute power laws. That's where you can see this coefficient. And amazingly, beautifully, it doesn't depend on anything except for this extreme diffusion coefficient, and it's completely general. Any model that has a sort of space-time decorrelation, you should be able to use the method, use moments or whatever, and compute the coefficient corresponding to it and prove a limit theorem of this sort. So it's a much more general, universal.
But then you use the Dirichlet.
That was an example.
Okay.
Yeah.
But again, that should be.
So really, it's any. I give the Dirichlet because, saying that I take a law on laws, like,
Okay.
I take a sample of a measure on measures is a little abstract, but rather I just take a Dirichlet. That's a little more concrete. So, but really, you take any model that you want that's somehow homogeneous in space and time in law, and has some space-time decorrelation, mixing conditions in space and time. The same picture will hold.
These mappings exist in higher dimensions?
Yeah. So in higher dimensions, yes. So you certainly can do something like the replica method there. Of course, the moments become a little bit more complicated. But I think we can justify showing that in some scale, again, a long time scale. Actually, it's not even that long. In higher dimensions, the long time scale kicks in even earlier. I think that we should be able to show a universality result as well in higher dimensions. And compute the coefficient in that context as well. We haven't completely done this, but the picture is coming to focus. Yes?
For your lecture, I have a question on your last lecture about the local time. It's before about the variables.
Yeah. So for which case? In this picture, or in the discrete?
Discrete.
Okay. So here's yes. I'll say a drop more. When I compute the second moment, I do a sort of replica. I represent each one of these these probabilities in terms of an independent random walk given the environment. Okay. And then I interchange the expectations. And again, as long as those random walkers are apart, when I do that interchange, I get a pair of random walkers R1 and R2 that jump independently according to just the averaged environment. It's only when they're together that they jump according to a different law. And that's this sort of expression, this product of Cj and Ck. Now, in order to show that the right-hand side converges to this exponential of the local time, what I need to do is I first need to do some exponential tilting of this system. I even needed to do that when k equals 1 in order to get a Gaussian. And when I do the exponential tilting, what I really want to do is I tilt it in such a way that away from the origin, things are converging to Brownian motions that are independent. It's just that there's some additional contribution at the origin. It's not exactly behaving like a Brownian motion at the origin. The additional contribution comes exactly from this coupled probability. And so what you have is that there is a sort of discrete local time. Every time my two random walkers are together, I get a little bit of local time in my formula according to that thing. And I need to now add that up over all time, kind of integrate that over all time and show that that converges to the analog in the Brownian setting. Now that is actually a little tricky because you have some pair of random walkers, you know that they converge to Brownian motions. That doesn't imply that their local time at 0 converges to the local time of a pair of Brownian motions. In fact, you can come up with very simple examples where it converges to 0, right? If your two random walkers are somehow on different lattices, one is on the even lattice, one's on the odd lattice, they never have local time at 0, or the difference, right? So what you need to then do is kind of study more subtle properties, and that's where you end up using this Tanaka formula and some study of the sort of local invariant measure for the gap process. So this, what's hidden in this slide, and I won't, we can talk later, but is exactly how, and this is a general approach, if you have two random walkers that have some sort of, and you're looking at how the local time converges to the Brownian local time, this is how you do it. You define a discrete Tanaka formula, you identify the thing that converges in red to the Brownian local time, and then you relate what I call a local-ish time, which is not exactly the local time. I relate that using the invariant measure of the gap of the two random walkers to the local time at 0. And that's ultimately, by unwinding that, that's how you get this coefficient.
Here, because we are for the break, and thank you.